particle travels around a circular path having a radius of 50 meters. If it is initially traveling with a speed of 10 meters per second, and its speed then increases at a rate of 0.05 times velocity, meters per second squared, determine the magnitude of the particle's acceleration 4 seconds later. Brilliant. So we have a particle. Let me just draw a circle center here. Let's do a little radius of 50 meters, and we know there's a particle that is traveling on a circular path about this center there at a 50 meters radius, and it has a initial velocity v naught, which is equal to 10 meters per second. The hardest thing on this question probably is not hard at all, is just understanding what they're saying when the speed increases at a rate of 0.05 velocity meters per second squared. Okay, so if we just look at the units, right? Look at the units, we see this is unit for acceleration, right? The other thing that's saying that is that this is the rate of increase in speed, which is the definition of acceleration. The third thing that tells you that is this v dot here, which is just another notation to say dv dt, right? So all those things are saying the same thing. They're saying that the way in which the velocity is changing is a function of the velocity. And so the faster it goes, the faster its speed is going to change. That's pretty much what's happening. And the whole question revolves around knowing what is the acceleration of this particle 4 seconds later. So we want to know at t equals 4, what is the acceleration? Okay. So the other thing we need to remember before we start is that because this guy is traveling on a circular path, at any given point, if we take the particle over here, for instance, it will have two components of its acceleration, right? The tangent component and the centripetal component, like so, AC and AT. Okay, so if we want to know the total one, we need to take the combination of these two vectors here. So my A, accounting for everything, a magnitude, AM for magnitude, squared has to be equal to my tangent squared plus the centripetal squared. All right, so what is our game plan on this question here? It's a simple question, as long as you know these concepts we just talked about. The game plan is, let's find out what is the acceleration at the time equals 4. That's going to be easy because we have the equation for it. But we also need to know the velocity at time equals 4, right? Why is that? Because we know the centripetal acceleration is a function of velocity. Remember, it's velocity squared over radius. So our game plan to be able to solve this question is, first, we find an equation. Okay, so we find a general equation. So general equation for both velocity, and acceleration. Okay, preferably not in terms of the unknown. Then second, we sub in t for time equals 4. And then third, grab AC and AT, and with that fourth, we use that guy there to find what is the total acceleration. All right, cool. So let's start. Let's write down the equation that we know for acceleration. We know acceleration is 0.05 velocity, and this is in meters per second squared, right? So therefore, if I sub in, if I know that this is dv dt, then I can simply say, well, dv divided by v equals 0.05 dt, right? Which allows me to integrate here from v naught, which I know, to any v that I want, and from 0, which is corresponding to v naught, to the t corresponding to that v there. This integral here is the natural log, right? Natural log of v over v naught. And that has to be equal to 0.05 becomes a constant, so I can sub in, so we can do, if I'm doing from 0 to 4, well, let's just do t times 0.05. Right? Brilliant. Now, what can we do? We can find the velocity at time equals 4, right? We just found the equation for the velocity, so now we can find sub in 4 and find the, I should have put this here, sorry. Sub in 4, find velocity. And with the velocity, then we can find acceleration. All right, so if I sub in here 4 at time equals 4 seconds, my equation becomes natural log of v over v naught has to be equal to 0.002, right, times 4, 0.05. You can take the both sides of the e, so e of the natural log is just going to go away both of those guys there, and over here I'm going to have e to the 0.2. So that means that my v over my v naught equals 1.22. And my v naught being 10, remember, this is 10 meters per second, means that my v at 4 seconds is 12.2 meters per second. Okay, now I have the velocity at, don't forget this is at time equals 4, right? Because I have that, I can grab my centripetal acceleration. Where's our game plan? Velocity can grab this guy here. And centripetal acceleration, where is it? Over here. So this will be simply 12.2 squared divided by my radius, which is 50, which gives me about approximately 3 meters per second squared. Unit-wise, let's just check quickly. We're squaring the velocity. The velocity is given in meters per second. So I'm squaring that, so we're going to have 2 meters in 2 seconds there, and we're dividing by the radius, which is in meters. Right, so meters and meters, we get meters per second squared. Brilliant. Now we need the tangent acceleration, and for that, we know that the acceleration is 0.05 times the velocity. So if we want at t equals 4 seconds, then at becomes 0.05 times velocity, 12.2. Tangent acceleration is 0.61 meters per second squared. Cool. And then on this unit here, if you just plug in the meters per second there, we don't know this unit here, so it will be hard to determine that way. But if you guys recall from the beginning of the problem, it actually says that over here, it says that the increase is given in meters per second squared, right? So we can be comfortable with those meters per second squared there. To finish off, we know that there's two components to the acceleration. So the magnitude of the acceleration squared is equal to the tangent squared plus the centripetal squared. So therefore, if I just want am, I'll just take the square root of these squares. So 0.61 squared plus, what was the other one? 3, about 3. And this is 306 meters per second squared. Okay, so just note that that's our answer right there. This makes sense, right? Because if you look at it, one is 3, the other one is 0.6, right? So we're talking one order of magnitude different there. So what we have, if you look at it graphically, let's go back to my original drawing. Let me just copy that with my drawing. There it is. Just copy this. Okay, so what we have here, our situation here is something like this. We have the center there, you have the path there. Let me get rid of this velocity here. Okay, so what we have is we have two components of acceleration. The tangent one, which is going to be like this big, I guess. Okay, 0.6. And we also have the centripetal one, which is going down. It's going to be way bigger, like this. Okay, so put this to the side. So when we take the magnitude of it, the contribution of AC is way greater than the contribution of AT, right? So we would expect the value to be closer to the one on AC than the one on AT, right? And as a matter of fact, the contribution of the AT is simply 0.6 on this magnitude, right? Because we know that if we completely cancel this one out, square root of 3 squared, it's just 3, right? So if we only had centripetal acceleration, we would have 3 meters per second squared as the magnitude of this particle. But with the contribution of AT, we get the 0.6 additional there on the decimal, right? Cool. If you have questions, let me know.